Yeah, and thanks to the people who pay for everything. Okay, right, so as Joseph pointed out, this is a three-part talk. The first hour is general material about reasoning and my research project, which has been going, as Joseph pointed out, now for 27 years. It's like having a baby, and I've brought it up. And then there'll be half an hour which is aimed at the students, which will be tutorial, and then there'll be an hour on the terrace drinking beer, which is aimed at me. And so we'll work through that. So what's this story all about? And I'm not quite sure of everybody's background here. How many are students in Joseph's course? So I can get a count. Like 5, and others are around here. And I don't know how many people have got a strong background in logic, so I'm going to run over things. And if you get bored, don't worry. This talk's got lots of components. You'll only be bored for about 2 minutes, and then I'll move on to a new topic. So it's not one of these things where I do lots of math. All right. So, as the picture shows, what is automated theorem proving? What's this all about? Here's how I see it. This picture over here is that the world has problems. One of them is called Donald Trump, but I'm working that one out. And often what you like to do is take a world problem and find a solution to that, which is nice, but that's difficult in many cases to do directly. You know, if you're trying to do something in religion or geography or sociology, sometimes there aren't the techniques available. So logic is the solution to everything, is to take a world problem, convert it to a logic problem in some encoding, apply an automated theorem proving system, a reasoner, get a logical solution, and extract a world problem, and everything's all right again. So how does this work in a little more detail? Sort of the basic idea is this: you've got the world, you need to describe the world, whatever it is, something in management or something like that, as a bunch of axioms in some logic, in a formal language. Some problem you want to solve, convert that to be a conjecture, something you want to prove, give it to one of these magical programs written by people with very, very large brains, and then get out a proof, which you then want to introduce to your solution. And there's various sides to this story. Firstly, you're looking for proofs. Given the axioms, can I inevitably conclude this theorem? You also want to say, given these axioms, do I know for sure that this is not a theorem, this is not a solution to the problem? You know, it's sort of Middle East is the problem. You know, the war in the Gaza Strip is definitely not the solution. You'd like to be able to deal with that. And in the classical sense, which I'm dealing with now, is you want to know that your description of the world is somehow consistent and reasonable. And so this is roughly how the story goes in terms of the computing technology. You have your axioms, the thing you want to prove. You give it to one of these fantastic programs. And if it says yes and gives you a proof, you go, hallelujah, we've got a solution. Or it might say, no, that's definitely not provable. At least you know you're going down the wrong road. A lot of the time you gave it 5 minutes and it says, well, I don't know, that's too hard. And this is standard story. This is normally implemented by proof by contradiction. Take the axioms, the negation of the conjecture, and look for something that says this is inconsistent. And again, it'll say either yes or no, and quite often time out because the problems are too hard. And I mean, the students will know about this, and Joseph will attest to this. The third thing, as we pointed out, in the classical sense, you need your axioms, your belief system to be consistent. So there are tools where you can give over your axioms, your description of the world, and it will tell you, yes, your description is consistent, or no, your description is inconsistent, you have contradictory beliefs, or again, time out because it's too hard. So that's what we're working with, that's the sort of the setting. And again, just to make sure that we all get the idea, here's some, like a toy example we can look at. By the way, you've got to watch the jokes, they're really good. If you get bored, just watch the pictures, because there's all sorts of good stuff going on. Anyway, no, don't, you won't watch anything. So here's a little problem. So here we write, here's the things we believe. The United States is a country, the capital of every country is a beautiful big city. There is some city that is the capital of the United States. Every big city has crime. A big city is also a city. There you want to prove that there is some city that is beautiful that has crime. All right, and if you sort of sit and squint your eyes at that, you'll probably agree. But so you can write this out, and here it is written out in first order logic. For example, this says for all C, if C is a country, then The capital of C is a big city, and the capital of C is beautiful. So it captures that sentence there. And most of you familiar with this sort of stuff. And what we want to do then is take that logical description and be able to feed it into one of these magical programs. And so you write it out in a sort of computer syntax, and this is my syntax that sort of most of the provers in the world use now, and you can hand it over. So if I took this, I'll copy it, and I've got an interface that we can do some proving. Here it is here, paste it in, whoop. There we go, and choose one of these magical tools. This is all available for anybody to use at any time, paid for by the taxpayers of the United States of America, to whom I'm grateful. Let's take this, Stefan Schultz's system, and we push go. Some magic happens in Miami, and voila, here out comes the proof. And this is actually then the solution that will prove to you that there is some beautiful city that has crime, and if we did a little bit of post-processing, we could make that look more human readable, and I'll show some ways to do that. All right, and so I've got examples here, and this is what we'll be doing with the students in the last half an hour, is going through these 4 different logics, starting off with propositional logic or Boolean algebra, which is not very expressive, but you've got very powerful tools, moving up first order type, first order, up to higher order. The languages get more expressive, so you can say more subtle things about the world, but then the tools are more and more complicated to code up as computer programs, and you need people with bigger and bigger brains eventually to deal with that. The sort of things that we're getting interested in at the moment is looking at topics of privacy and ethics and law. How do you encode those? The new European law on privacy, of course, is a big deal. Every company around has had to change its processes, and how does the company know formally that it's meeting the requirements of the GDPR? And so encoding that is a useful thing, encoding notions of law. So when somebody does end up in jail, locked up, then you want to know for sure that they definitely have broken some law and the rules have been done right. And that's where things are moving at the moment in my world. I'm interested, not about penguins. All right, so to get you further motivated, what are these tools used for in the real world? Okay, not just us academics playing in little circles is what we're doing. So the origins of this, the origins of the use come from the 60s. People in Germany and England and Argonne in the USA started dealing with this, and one of the famous results, if you're into math, is that every Robbins algebra is a Boolean algebra. This was posed by Tarski in the 50s, and none of him or his students could prove it. And then eventually Bill McCune wrote a program, one of these magical programs, and managed to prove this open math problem had been open for, when he finished it, about 40 years. And that's quite an amazing result. Things in geometry were done in China by Wu. This is the work of Bob Verhoff, who's coming to visit here next week, of Ian Luke's very deep theorems in mathematics, where the proofs are very, very long, thousands of steps long, and finding new results in math. This is Joseph's work, the Mizar material that Joseph and I did some years ago. And interesting, any people who use Mathematica, I guess if you're a scientist, embedded into that is the Voltmeister theorem prover that was written at Max Planck Institute in Saarbrücken by Thomas Hillenbrand. It's now embedded into Mathematica as one of the modules of that. But there's no money in math, so let's abandon that. How do you make money? So the big commercial application of these tools and this technology now is in software, verifying it, and there's interesting projects. The key project, which Denmark is it? So they found, so in Java, people program in Java, programming language, and there's a sorting algorithm that's built into it to sort things, and it turned out that they found a bug in the sorting algorithm of Java in the Java libraries using this technology, because it's in the bucket sorts, and they found some cases where you could give it an array and it wouldn't sort it even though you had run array.sort on it. And that's kind of nice, because that affects your life, because your telephone has your contacts sorted. And imagine if your phone, you say, go, sort them in alphabetical order, and it's not there. You say, I can't find my contact, and therefore I can't do things. So it's important. Right, the Microsoft guy, this is a company, this is Ron Artham's company that works on this. Microsoft, of course, is famous for this sort of stuff, both the English branch and the US branch, for finding bugs in device drivers and in decoding of codecs for video in that. So this is where the big money's at the moment. If you want to become rich and famous and buy me a boat, okay, yourself a boat. Then the same thing is done for hardware, especially when Intel discovered that they couldn't divide properly, and that was a nasty event. There's a lot more work now on using ATP, theorem proving technology to verify chips. Intel, Cadence in the US, Oregon. That's good. Getting to more interesting things, reasoning about processes, particularly in factories. You know, you've got machines. What you want to make sure is when the big blade comes down, nobody's hand is in there, because so you have some proof that no hand can be where the blade is going to come down because they're holding two buttons, those sorts of things. With robots doing welding, you don't want two robot arms to cross, which is partly theorem proving and partly geometry. Amazon, of course, if you tell them now, if you go to Amazon and you're using Amazon Web Services, your data is private and secure, and they do a lot of formal work on that. The semantic knowledge-based system, so this is reasoning about the big, bad, ugly world we all live in. This was early work Cite by Doug Leonard, and then Adam Pease with the Sumo project, trying to capture very general notions about the world, which turns out to be messy because the world is contradictory, and you don't want the world to be contradictory because the programs don't work. Nice problems. I think many of you would have seen Ben Gertzel when he was here. He came and gave a talk, and so they're using theorem proving so that to solve, solve the reasoning problem and solve the world's problem. What's their motto or something like that? Interesting guy. And then we get into more fun stuff. So in biology, they took, in the US, the schools, high schools, have a textbook that all schools use consistently for biology, and they took that book and tried to encode it. And they encoded about 70% of this high school textbook into a formal language, which we then proved consistent, and then tried to do the high school exam questions based on the formal encoding. And that's a nice project, you know, so getting computers to do what high school children can do, so you don't need high school children anymore, or something. All right, legal reasoning, this is what I was talking about. The guys in Luxembourg and this company, Lex Cognitans, taking legal arguments and making and encoding them formally. Very nice thing. I thought this was a great project when I found this one. The acronym's too good. Consistent Rational Arguments in Politics, the CRAP project. Fantastic. So they're taking political discussions and arguments and then encoding them to make sure that there's not crap going on. Very nice project. This is Carsten Sherman in Denmark. So what they do is encode properties of voting systems and elections, and then you want to verify that the election has some certain fairness properties. So for example, you would like to make sure that the box full of ballots is never alone with one person from one party, because then you stuff the ballot box, so there's always at least two people. And that's kind of nice. I know they did the election in Egypt a few years ago, this group. And here we are talking about the GDPR. There's a company that works in that. So I hope this has sort of motivated you to see that there's use, but now let's move on. So I don't want to spend a lot of time on this. The key story is the picture of the washing machine here, is that these tools that do this reasoning, automated theorem proving, are complicated. As I said, people who write them have huge brains, because it's a mess of data structures and algorithms and techniques. It's not something you sit down one afternoon and whip one off. So there's famous ones like Otto, which comes from the Argonne group. The E, the one I just ran now from Stefan Schultz. The big famous one, of course, is Vampire from Manchester, which seems to win all the competitions. Voltmeister, the one that's caught inside Mathematica. I've got a few others here. It's not important, all the details. But as you see, as you go on, you get to these higher order logics, you get less and less of them, and they're complicated. Satlax was originally written by Chad Brown down in Joseph's group over there, and other things. So the point I want to make is these are complicated, difficult tools to write, and in some senses they can be difficult to use. And part of what my work is to make them easy to use, to hide away the insane deep computer science from people who are interested in politics or sociology or geography, and make it easy to use these tools. And that's what I want to talk about mostly. So I have this big infrastructure, but I have to, so I wrote a paper about this when I first started with, the guy who started with me, And this was the most fantastic paper review I ever got. You have to read it. The reviewer, like most readers of the AI journal, believed the style and systems as compared here, blah, 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 have their roots in the 70s and 80s and are misguided, intellectually frozen in a time warp of the early days. This is what my reviewer wrote to me. Hence, these competitions are not only a waste of time, counterproductive, they lure the young researcher into a style of work that's essentially wasted. The organizers, the authors of this paper, should be forced to drink the poison cup of Socrates for corrupting the youth. Now, that is a good review. Eventually, this paper was accepted, and this guy did do it, but I thought it was a lovely thing to write about it. So if you are in theorem proving, don't believe this review. Okay, so what is about this TPTP? TPTP, and by the way, this should become your home page on your browser for the future, tptp.org, because it's the only thing you ever need. Once you've solved theorem proving, we can solve the world problem. It stands for thousands of problems for theorem provers. Historically, people were writing these computer programs to do theorem proving and testing them badly, evaluating them on, they would choose the 10 problems they could solve, get great results, and publish and say, yes, I am wonderful. And then, but worse, people would choose the wrong 10 problems, they'd have a great idea, choose the wrong 10 problems, get bad evaluation results, and give up on the idea. So Christian Suttner and myself in Munich, we started off collecting problems and building this framework for evaluating theorem proving programs. And the first step on this is the TPTP Library. Quick, it's a joke. Gone. You gotta be quick. All right, so what was this? We just wanted to collect problems and have them in a standard syntax with documentation, just getting organized. No deep science, we just got everything organized. And we started collecting them, and the first release was back in 1993, so this is 26 years ago we started this game. And we're now on release 7.2, this slide's one slide out of date, about 20,000 problems, 22,000 problems that people can use. These problems are fully documented, well analyzed, their properties are known, and therefore if you're testing your new piece of software, whatever idea, using machine learning or using some new techniques, you know you can get a proper test bed and get results that are meaningful. If you look at an example of one test problem, here it is. This is something in set theory. You can see over here. These are all comment lines. This is in set theory. It's the product of an unempty set of ordinals is an ordinal. Chad, I don't know what that means, but is it true? Yes, it is. All right, so the way it's encoded is a theorem. What we do offer are these ratings in the range from 0 to 1, where 0 means really, really easy, and 1 means no theorem prover that I know about can prove it. So this one is it's a pretty hard problem, that 0.93. And that's a useful thing to do, because if you're a student and you're writing your first theorem prover, this is not a good test problem. You're not going to solve it with elementary techniques. But if you're getting on and you're at the cutting edge, you don't want to try the easy ones, it's wasting your life away. You want to look for difficult things to try and prove. So we provide ratings. Bunch of syntactic measures, useful for machine learning techniques. I'll talk about these SDCs. Then it includes some axioms. This is just like standard programming stuff. And then here are the axioms. So for example, here, what does this one say? It's in first order form, it has a name, it's an axiom. For all A, B, and C, if A is a subset of B and B is a subset of C, then A is a subset of C. So it's sort of readable in English style if you're in the first order language. So this TPTP language, almost all theorem provers in the world can read it now, and that makes it easy for tools to interconnect with each other. People can write things in one language and know that there's a bunch of tools that will talk in this language. I would say there's a competing language called SMT, and when you see it, you should just say SMT, just say no. No, they're a different group, they've got more brackets than me. All right, and this is a provable thing. So we started collecting these over time, and it's been growing and growing and growing, and as I just mentioned, if we look at, there we go, here's a picture of the growth over the years. You can see the year numbers down the bottom here. This top line is, the bottom lines when I've divided up into different languages, propositional, first order, type first order. But here's the growth over the years as we've gone along, and we've gone up to 20-something thousand problems now. So this is very much in the Yahoo idiom, is that this database of test problems is curated. Every problem I've looked at personally and checked it and formatted. This is not just throw anything in and pray that it's okay. So it means if you're a person testing software, you know you've got a well-organized and curated test bed. All right, and it's all available, and you can cruise around online. Just go to your home page, and which is this, and everything, and you can read this part, which is critical, okay, because I need a bigger boat. My 30 foot's not enough. And you can then, if you want to go look at a problem, you can cruise. All of this is blah, blah, user web interfacey kind of stuff to look at things like that. All right, so we did that. And then one of the things we noticed, having collected these problems as we went along, is that theorem-proving programs would print strange things which didn't really tell you what they had established about a particular set of axioms and a conjecture. Because a lot of them would just print, you give it to them, they'd write yes. Well, yes what? You know, the thing. And this is all over. And so we started thinking about what sort of information you need to have when you feed it into a theorem prover, where we have problems, and then what sort of information you'd like to get out the other side in a formal way. And we built an ontology for that, which is the SZS ontology. It's a bunch of ice creams. No, so we look at things like this. For if a theorem prover is successful, well, you've got an ontology. There's the big picture. Success, and the nice case that we all like is this piece in the ontology there. Yes, that's a theorem. You know, we know exactly. But it could be a theorem for multiple reasons, and so there's a lot of sub-reasons why something could be a theorem as well in terms of the semantics. So this is all, and the theorem provers can print out exactly one of these ontology values, and that means the end user, you or some subsequent tool, knows exactly what's been established by the tool. As well as for success, as I mentioned earlier, often they say no, something went wrong. And you want to make productive use of failure. And that's, we have an ontology for theorem proofs to say, this is why I couldn't do anything. I mean, the obvious one is I ran out of CPU time, but it could be a bunch of other things. And we also have standards for how you write out a proof, what is exactly how a proof should be written, how a model should be written. And that means because this standard language is the same language for input as it is for output from a tool, you can pipeline the tools together in good old Unix pipe fashion, because the languages are compatible as you go through the pipeline of development. Then I got bored, and I thought, well, what next? And so I'd collected problems, so I started collecting solutions. And so I built the TSTP, which is thousands of solutions from theorem provers. So I've got, as you saw in my interface, I've got about 80 theorem provers, because everybody gives them to me because I do all this stuff all the time, and 20,000 problems. And then we built the star exec site and some computers and just ran the whole matrix to see what happens. And we've got all the results, and it's all totally available there. And firstly, that's useful. For example, Joseph's work, machine learning. If you've got lots of solutions, lots of proofs, you can then machine learn from them to learn techniques, how to do things better. It's useful for people developing. You say, hey, here's a theorem I can't solve, but your one can solve it. I've got your solution there. You can go and look at the solution, see how that solution was created, and then improve your own tools. So that's another use of this. And yeah, just nice to look how things are proved. And so how did we do this? We run all the theorem provers on all the problems. And you say, well, if it doesn't solve it, why don't you just give it some more time? You know, maybe 5 minutes is not enough. Just give it 10 minutes, or give it an hour, or give it 3 weeks. And I see Chad smiling. And we were discussing earlier, yes, today, about giving more resources doesn't help in theorem proving, more hardware. And this is something, so we did a quick analysis, and this is the picture. What we did for each of these lines corresponds to one of these tools. So this end one here is Vampire, the almighty Vampire, yay. And we took all the 20,000, or that stage 6,000 problems, this is one slice of the TPTP pie, and ordered it by the time taken. And as you see, except for this green guy, which we can talk about, almost all theorem provers say, this is time it takes to find a solution. It's easy, easy, 1 second, less than a second, less than a second, less. Oh shit, it gets difficult suddenly. It just suddenly happens. And these curves, we look at that, this is much sharper than exponential corners there. And this is like that book, The Peter Principle. People know the book, The Peter Principle? It's a book about management and companies. If people are good at their job, you promote them, and they're good at the job, and you promote them to the level of incompetence, where they're then bad at their job, and they sit there and they just do badly. And there's no notion of, well, push them back a level to where they were good at their job. It's a terrible, terrible thing. And I think, well, am I a victim of this? I don't know. I mean, look at yourself and say, am I a victim of this? I've been promoted to my level of incompetence. But this is what happens with these theorem provers. They can do things, then they hit their level of incompetence, and it just becomes too difficult. And so if you look here, this is seconds of CPU time. Let's just take Vampire, it's easy to read. After 150 seconds, really not much happens anymore. Similarly here. So 150 seconds is enough. Probably 60 seconds is enough. After 60 seconds, you start hitting memory issues and the search space blows up. And you don't have to worry anymore. So I gave 300 seconds on these tests. And this green guy, who is the green goddess over here? It's Isabel, because this is how he works. He says, I'll try one idea. Oh, that idea doesn't work. Let's try another idea. Oh, that idea didn't work. Try another idea. So he just switches different ways of doing theorem proving. You get this scalloping effect. What else should we talk about that? All right, so these proofs, I've got this huge collection now. And wowee, if I show you an example, you'll say that looks familiar, because it's pretty much the same thing. There's all the documentation. And here you see the formulae, and they look just like problem formulae are the same as solution formulae, and so the languages are completely interchangeable. All right, how are we going for time? 26, okay. So, trying to think what I should talk about. There's so many things I can talk about here. Let's talk about this. This is somewhat interesting. So I mentioned that for every problem in the test library, it has a difficulty rating. And you think, well, how do you compute how difficult it is to prove a theorem? There are some problems in mathematics which have, how many problems in the AIM project, Chad? 7 axioms?
Yeah, the 12 axioms is 7 main problems.
Yeah, and it's like, it's really small. You could sit down and read it. Anybody who knows any algebra can read this stuff. And you think, oh, well, that should be easy to prove theorems about that. And it turns out that it's very, very difficult to prove these difficult theorems in that. On the other hand, there are problems that look very difficult and turn out to be very easy to solve. So any judgment a human makes is probably going to be wrong. So here's what we do. And this is also a technique that can be used for other things. If you've got a data set and you want to specify how hard the problem is. So if you think of this picture here where I'm moving my cursor as being every dot represents one problem. And some of the problems, which I've done in colors, are biased because people submit problems to my library which says, I'm going to put this one in because I know Joseph won't be able to solve that. And so we get rid of those. We get rid of those. And then what I've done is divided the TPTP world up into problem classes. And we saw that slightly earlier. So what a class of problem is, problems that are have the same semantic and syntactic and semantic characteristics. So it's theorems in first order logic with some equality might be an idea. And so they're types of problems, same sort of thing. It's like when you go to the shops, there's the fresh vegetables, the cold things, and the tinned food. It's just different types. So we split them up, and we focus on each one of those categories one at a time. So we just pick one of them. So if I zoom in, so here we have each of these circles represents a theorem prover, and the dots inside are things that it can prove within 300 seconds, and we know that that's good news. So we can see, for example, this green guy is a big guy, and this purple guy is useless. He can only do a subset of the green guy, and the orange guy can only do one thing, and he's a subset of the red guy. So the first thing I do is I take these systems that solve a strict subset of somebody else and throw them away. All right, and like that. So we get rid of them. And so what's left over is these. And then from those you can start looking at of how hard the problems are. So if we look at this, so for example, the green guy, what fraction of the systems cannot solve the problem? So in the yellow area, the rating is 1 because nobody can solve it. In the intersection in the middle, it's 0 because everybody can solve it. And then the others. So this red theorem prover, these problems in the red area are all rated at 0.66 because 2 of the 3 solvers cannot solve them, like that. The light blue and the green guy cannot solve these problems. So that gives that, and the nice thing, and this is where the poo hits the fan a little bit, is you can then use that. We throw away the very easy problems, and we throw away the very difficult problems because they don't differentiate between the systems. And what you get is a rating on each theorem prover. It's the fraction of the problems that it can solve over there. And so you see here that the green guy is the strongest. He's a 0.55 solver. And that's useful, I was showing this morning, is if you've got a problem you want to solve and you don't know which theorem prover to use because you're new to the technology, I can, in my interface, you say, give me the problem, I can use this sort of information to say, I recommend these person. It's like a music recommender on Pandora or whatever you use, Spotify. I've got a theorem prover recommender as well. And that's a nice tool to play with. So maybe we can look at some of these tools. All of this stuff's available. As I said, you can run it through an API, or you can run it through, I can give it all to you if you want. It's free, but it's a pain. Or you can just run it in your web browser. So let's do that. So this is the web browser interface to this. Just go to your home page. Whoops, daisy. Do that. So the first sort of thing you can do is take a problem from the TPTP library. So you can upload your own, as I showed you, various ways. So if I take this one, plus 0, 0, 1, plus 1. And the simplest thing to do, as I showed you before, choose a theorem prover, and I know E is good for that, and push the go button. Stuff happens in Miami where it's sunshine and electrons just have to come back from the beach, do some work. Where they go again, and you get a proof. And that's kind of hard to read, isn't it? Yak. So you can turn on some more buttons that just make it look pretty. There you go. See, and you get a whole lot of stuff, and you get a message saying if you push this button a lot, you should donate money. And you get things that becomes readable. But even that's human readable, it's not going to be readable all the time, so you might have to do a little bit more. But before I show you how to do more, you might be a new user and you don't know what to do. Which theorem prover? Is it E or decider or something? So you can just push the recommend button, dot up, and it tells you here in order with a rating of which systems are most likely to be able to solve that problem. So if you've got a new problem, you can just take my recommendation and it's statistically okay. You can be even lazier. You could just say, run the top 3 systems in parallel. And so my tools will then take your problem, work out top 3 systems, and then just run them in parallel. And the first one that finds a solution, it prints out the solution for you. A bunch of debug as it goes by. So the point I'm trying to drive at here is that within this interface, if you're not a theorem-proving geek, but you'd like to use it, you don't have to be a theorem-proving geek. The language is simple, and the tools hide away the insanity of these people with large brains and the stuff they write. We saw earlier a proof that looked funny, and there's a tool which I would normally be able to click in, but nowadays people don't trust applets on their web browser anymore. So I have to run it on the interface until my student finishes the new implementation. Right, so this then is a graphical rendering of that proof we saw earlier. And now it becomes easier to understand it. This is the Aunt Agatha problem. So firstly, let's go and look at the Aunt Agatha problem. You might recognize it. Right, so here's the story in English. Okay, so this is somebody who lives in the mansion killed Aunt Agatha. Agatha, the butler, and Charles live in the mansion. They're the only people who live there. A killer always hates his victim and is never richer than his victim. That's a demographic. Charles hates no one that Aunt Agatha hates. Agatha hates everyone except the butler. The butler hates everyone who's not richer than Aunt Agatha. The butler hates everyone that Aunt Agatha hates. No one hates everyone. Agatha is not the butler, therefore Agatha killed herself. All right, now if you stare at that hard enough and squint your eyes, you could probably conclude, yeah, that Agatha is suicidal. All right. But you need to squint your eyes. For a theorem prover, this is easy. So we can start writing down the axiom. Here it says, whoops, this is in my syntax. There exists X so that X lives in the mansion and X killed Aunt Agatha. Here we see Agatha, Butler, and Charles live in the mansion, and they're the only people that live in the mansion. Here we say, for all X and Y, if X killed Y, then X hates Y. So you can see we can convert this English into logic. And then I ran the theorem prover, and the output of the proof, which is the output I showed you earlier, is this. And you can start doing it. And even if you don't like looking at proofs, there's cool flashing lights. So just take your acid tabs and play with it. So across the top here is the input. So these are axioms, these triangles. There's the thing to prove. I don't know if you can see the writing down the bottom here. But that says that's the conjecture that Agatha killed herself. And it shows you, well, it shows you that how axioms are combined together using classical reasoning till eventually there's a proof by contradiction here. You can see the conjecture has been turned upside down, which means it's negated, so we're going for a proof by refutation. And if you highlight a node, you can see which axiom it depends on. So this node in the middle of the proof, which is like a lemma in mathematical terms, you can see where it comes from and you can see where it goes. And then we have this magical tool. So we were using this on the AIM project, and the proofs were huge, and my software just eventually was loaded. But then you couldn't see it because all the dots were real tiny. And so we did some work, which is this light bulb. Something's happening. You notice now the dots have changed size, and what it does, it evaluates each node in the proof for interestingness on a bunch of characteristics. What does it mean for something to be interesting? We can talk about that if you want to. So you can then go like this and hide the boring parts of the proof. That's kind of nice, and redraw it, and you get a proof summary. And what you're showing then is like bigger steps as you go through the proof. You're not looking at all the micro deductions, but you're looking at rather large steps, which gives you the lemmas that are interesting. So for example, this one here, oh, there's a big one. That one says, either X is the butler or the butler hates that person. Here we go, that's a nice one. There, you can't read the writing, maybe it says the butler doesn't hate himself. It's one of the conclusions as you go forward there. Of course, if you've negated the conjecture, anything that follows from the negation of the conjecture is going to be the opposite of your intuition because you've negated the conjecture. So you can turn off just look at things that follow from only the axioms, and those are lemmas in a mathematical sense as well. So as soon as Mr. Joseph Masterjohn gets his act together, this will be back integrated into the web interface for you to play with as well. All right, so now let's talk a little bit about some of the things you saw there and the technology that's underneath them. The first thing is when a theorem prover written by a person with a very large head prints out a proof, you say, well, why should I trust it? I mean, it's written by a German. You turn your back, they'll take your sausage and drink your beer. So you don't trust the proof steps. And so you say, right, how should I trust it? And so there's several people have worked on this sort of story, is how do you take a proof and make sure that that proof really is a proof that you can believe in? Because if it tells you at the end, go and buy stock in Tesla Car Corporation, that's got to be the right advice, because it might not work so well. And the problem is, as I mentioned, remember the washing machine? These theorem proving programs are complicated, and bugs happen. I mean, it's just part of the life of complicated software. So rather than trying to look at the software and do some testing of this washing machine, rather what we do is look at their output and check it. And so this picture shows why. I mean, here's why, because it's like there's bugs. So look at this. Here's a proof. You've got your input problem that has 5 formulae, and you do each of these, you can see deductions there from number 2 and 3, you get to L2, and from L1 and L2 and D1, you get to D3, from D3, D4, and L6, you get to F, and so there's a sequence of inferences going on. So what you can do in the first case is take each of these inferences, like from L1, L2, D1, get to D3, and generate a new theorem proving problem. It's a sub-problem, and typically much easier than the original whole problem, and then give that sub-problem to somebody you trust. All right, so who do you trust? I trust Otto from Argonne Labs. Why do I trust it? It's been around unchanged since 1995. It's not going to change because unfortunately the author passed away. It's been used by hundreds of people, lots and lots of times. The bugs have been found empirically. But if you don't trust Otto, you can choose your own trusted system. If you trust Coq or Isabel, why? I mean, these are software masses. Anyway, and test and just check every inference in a proof. There's something else you have to do, is you need to make sure that the leaves of the proof do actually correspond to what the input problem was. Because I've seen this, is you give a complicated problem to a theorem prover, and it kind of ignores the problem, or the parser is not working right, and it proves something else. And the proof is completely correct, all the inferences are right, but it's of a different problem. So you need to also check these, that each leaf of the proof does come from the input problem as well. And so that we have a tool that does that. Go back here. So I'll do that same example again that we're playing with, the Aunt Agatha problem. Like that. And let's say we want to check if E has got any bugs. So we can then send it through to the next interface. The proof is going to go through to the next interface. And this is an interface for examining proofs. And there's lots of things you can do. And one of the things you could do is say, hey, go and verify that proof. Click the verifier, and there's other tools, there's massive stuff. And we go, bam, and what you'll see as it goes on, stuff happening in Miami. Why am I not getting anything here? Well, it does what I'm showing you in that picture. It goes first and checks that the leaves of the proof come from the problem, and then each inference, there we go, there's the output. And to see it's going through, yes, I've checked that the leaf axioms are satisfiable, which is what you want. Otherwise, you get proof by contradiction just from the axioms being contradictory. And then goes through, there's some warnings that some things that it can't do. And so it's checked it, and yes, it's verified the proof. Now that's quite nice as well. So if you're developing a theorem prover, and I'm talking about students if you ever do it, and you don't know if you've got bugs, one of the things you can do is take your proof output, hand it to this tool, and it will tell you if you've got mistakes in your inferences. There's this notion of interestingness I spoke about. This is quite nice, and we were talking about this at lunch today. If you've got a bunch of axioms, can you forwardly generate lemmas that are interesting and useful in some sense like that? And we have a tool for this as well, the automatic generation of interesting theorems, written by a student ages ago, Yi Gao. And what are the things, well, what do we mean by interesting? What makes a statement in a proof interesting, a step in a proof interesting? And here's our measures. Firstly, is it obvious? things that take one inference are not really that interesting. You know, if A implies B and you know A, therefore B, well, you're right, yeah, it's not exciting. So we want fairly large, complex piece steps. The weight, how many symbols, large, complicated structures, like the constitution of a country, is much more interesting than the cat set on the mat. So weight is an important factor. Complexity, how many different symbols? If you use the same word over and over again, if I keep saying over and over again, over and over, I'll say that over, you say, gee, shut up, Sutcliffa, because it's not interesting. But if I talk about many different concepts and put them together, then that becomes interesting. And also surprising, unexpected co-occurrences of symbols. It's kind of funny when you get a sentence and you talk about political wisdom and Donald Trump in the same sentence. That's, whoa, that's a surprising combination of terms. So that makes it interesting. We've got some stuff on information theory and variables and focus. So we have tools for this to generate interesting theorems, or given a proof, to take a particular lemma and say automatically how interesting it is according to these measures. And I can talk more about that in detail if you want. Okay, and I should that. All right, so a little bit about applications, places in the world that have used all of this TPTP technology. The first project I did with Bernd Fischer at NASA in Ames is they had software that was, they had programs that generate software to go into the space, the NASA, the Hubble Space Telescope kind of thing. And when you put software into a satellite, it has to be right, because you can't reach up and do Control-Alt-Del, right? Because it's too high. And so what they do is they generate this software, and the software, then the people who did quality control at NASA said, we don't trust this software, it was written by a computer. How can we trust it? Of course, they trust programmers, you know, like it's so reliable, but okay. So what we did is this. Did this picture expand? Yes, there it is. So you take a problem specification, a piece of the software for which you want to program in software. The software comes out in C programming language, and some policies on safety, like you will never go off the end of an array or something like that. Then you produce the C program using synthesis, and then from that we have annotated code, which then can be reduced into verification conditions that are written in first-order logic. And then we run it to a theorem prover and a proof checker. Why do you need a proof checker? Well, it's funny, we ran the theorem prover on this and said, look, yeah, this piece of software that focuses the telescope, whatever, we've checked the proofs, and this piece of software is good. And then the people at the FAA said, who checked the proofs? And we said, no, we said, well, we didn't check it, but we believe the theorem proof is good. No, you have to check the proofs. And so we used the GDV, the verifier tool, to do another round of verification. And eventually you walk into the FAA office, essentially with a large pile of paper, and say, there, and here's the proofs, and proofs that the proofs are proofs. And then they certify the software in C. So that was quite a nice project for real stuff. Here we go. Joseph, do you want to give this part of the talk? So this is when I first knew Joseph, and he was first exporting Mizar, and it was in the early days when it wasn't all quite as gloriously smooth as it is now. And we wanted to check the Mizar library. People know the Mizar mathematical library, big library of formal math. And so we did various ways of verifying that, taking out little proofs in Mizar library and checking each one at a time, and we got to a very high percentage of it being checked formally. That's quite nice, and again, you can see here we used that verifier, the viewer, to be able to look at the proofs and get to see if we got something interesting out of that. And here I'm looking at the proofs. So that was another nice project using TPTP technology. Sledgehammer, who are Isabel users? Any Isabelites? Yeah, a couple. And so you know the Sledgehammer tool within Isabel, which hands off sub-problems, and Isabel has built into it its own internal suite of theorem-proving programs. And additionally, Isabel talks to my stuff in Miami, the same as that web interface, just does it through programmatically. And so the benefit of that is that my theorem provers in Miami are typically most recent versions that are not already in Isabel. Isabel lags behind a bit in the development. And so using the external provers in Isabel, you get the latest theorem proving technology underneath that. And so That's quite used. So that's nice if you're doing formal development in Isabel. Here's a good one. Here's the religious story. Proofs of the existence of God. So if people are aware of the ontological argument, of course, several philosophers have dealt with it. Gödel, Spinoza, Alzheimer. And so there's a well-known one by Gödel. And so there's some axioms which you might think are reasonable, like God is all things that are good, and if it's good, it is part of God, and that sort of stuff. And then you do a proof that God necessarily exists. And this is a higher order modal problem, because you talk about possibility and necessity in this as well. It's actually only second order, I think, second order modal. And so the proof by Chris Benchmuller is the one I know about most. The original one was handwritten by Gödel, and you can see the original one. And then Zohar Manna, I think it was Manna who did the hand, he typed it up, got out a typewriter, and typed out the proof of the existence of God, and and then republished it. That was fine. He's at Stanford. And then so Chris Benchmuller then built enough technology to be able to deal with second order modal logic, quantified as well. So he took the typewritten version and coded it up and gave it over to the TPTP, and he couldn't find a proof. And then they found that there was a missing implicit statement that hadn't been put in the axiom, and Gödel hadn't formally written it down, and therefore Manna didn't write it down in this typewritten one, and they found that where it was missing, by using model finding, put it in, and then you can get a proof of the existence of God, which is very cool. And this got quite famous, of course, because if you announce to the world, I have a proof that God exists, the Pope is interested. And so this got into, if it's still up. All right, so this is in the online Spiegel, for people who know the German newspaper. What? Continue with ad blocker. Yeah, I agree. And I can't read the German, but there's an English version, and it says, Apple Macintosh proves the existence of God. All right, and of course, everybody, a Macintosh? Did you know Apple Macintosh? Nobody cares about the logic and the theorem proving it, just an Apple Macintosh can do this. I think Apple should have given Chris a free computer for that work, because it really did, somewhere here, in German. People, I don't know if anyone reads German here. Blah, 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 it's Gödel.
Second line.
Yeah, here we go. The MacBook. MacBook proves the existence of God. So I should be able to do it right here. So that's a nice thing. All right, boom, boom, boom. Oh, I should talk about the competition. I'm coming to the end here. So Joseph mentioned this. We've been running this competition for theorem provers since 1995. And so each year we have at the conference, either HCAR or CADE, we have the competition. And at the very beginning, how could we do it? I did it with this as Chris Suttner at the time, and we were sitting in the park after Nancy, and we had the TPTP to framework and the language coming together, and we thought, yep, we can run a competition. And we very clearly decided at the beginning that it would be 50% about the competition, who can solve the most theorems the fastest, and 50% about inspiring people and developing the technology. So we make a lot of effort every year. So we have T-shirts and gambling and a dinner and all sorts of stuff. We have horse racing to represent theorem provers. And what we found, and Stefan said it most clearly to me once, he said, you learn a lot more about how to implement theorem prover by sitting across a table at dinner than you do by reading people's papers. And so we really do try and provide an interactive environment where people, especially new people, can talk to the experienced old hands and get the ideas and understand how you write one of these tools and how you write them well. And so the first one was in 1996. Cool, look at me there. I had more hair. Jeff Pelcher, Tanel Tammet, there's Don Loveland in the background. This is at Dimax. Man, look at those pants. Amazing. So now it's an annual event. This goes on all the time. And the most critical thing is we have these fantastic T-shirts. You can see the T-shirt designs. Where do you come up with this stuff? That's for today, the TPTP Brewery one. Get saturated. This was, I think I was in a bad mood that year, so we did the guillotine. And this one, I think the joke is good. It says, this T-shirt is the worst T-shirt ever. Don't worry, I play here twice a week. And so you should enter. And of course, anybody can enter this competition. All you have to do is enter a sound theorem prover. None of them are complete. It must never give the wrong answer. So what you always write, you write a one-line Perl script, print out, I give up. Okay, perfectly sound, it will never be wrong. And then you pay your entrance fee, you get a t-shirt, you get a dinner, you get to meet everybody. It's a fantastic thing. So I encourage you to all join. We're going to Brazil this year, lovely destination on the beach. Am I selling this well? But even, I mean, just writing a quick theorem prover in Prolog is really only a week's work. And you can write something that will do more than nothing and get a t-shirt. I'm running out of time, maybe just one more details about that. All right, so this whole, right, there's beer involved always. So this whole TPTP thing, and as Jasmine said, this is a jungle of stuff. There's a lot of tools that enable you to do a lot of things that interact with each other in a consistent way with a consistent language. It's been very important to have the same language for input and output and have this curated library and the ontology so everything works together quite seamlessly. And I think that's useful. I provide online services, so people who are interested in the real world, in geography or biology or engineering or something like that, don't have to worry about the details of what's happening at the geek level. Provide a nice interface so you can think about encoding your problem and solving your world problem using theorem proving. For people who are into Prolog, you might know Richard O'Keefe, who wrote the book The Art of Prolog, and it's got that in the beginning of the book, you know, where they normally write, this is dedicated to my grandmother. He wrote there, elegance is not optional. So if you're in theorem proving, TPTP is not optional. A lot of people have helped me, and I mean, the people right here, Chad and Joseph have been great contributors to this project, and others, I'm sure. And I'm always looking for feedback and comments, and I'm happy to deal with people. I read email a lot. But I have noticed this strange effect that I did a statistical survey of people who use the TPTP. There was me, and here's Tim Bray, you know, the XML guy, to say no. Chris Sutner, who started the project with me, and look what happened as time went by when he went to industry. Are you doing the machine learning here? If you use the TPTP, you have one physical characteristic. And if you don't use the TPTP, lower row, you have another physical characteristic that's quite clear. Look who's guilty. You see, look at that. It's absolutely consistent.
You can see them in their flies, that's not fair.
Oh, whoops. But this is kind of strange because Chad was a mathematician and he didn't, but now he's a TPTP guy to some extent.
Yeah, I didn't use it enough.
Yeah, you didn't use it enough, but I did actually solve the problem. All right, so that's as much as I want to talk about for the first hour. If I can take some general questions, and then people who want to slide off can, and I'll do some more teaching style stuff for Joseph's students. Thank you. And if there are no general questions and you want to slide off, just go. I'll just stare at you.
Oh, okay, so...
Let's take a 2 minutes so I can drink something.
Yeah, so couple of questions, and then we will do the exercises.
Yeah. The students will work. And if you're here, you will work. It's not going to be sitting. This is interactive. Does anyone want to ask anything about this story? No. Chad slides off.
Yeah. Just make sure you stare at me and make it briefly speak.
Okay, well, looks like we're three.
All right, so you will ask the questions to the students.
Yeah, right.
So you asking the questions could have saved you from Jeff asking the questions to you. But, all right, we have the first question.
Yeah.
Okay, so you have a collection of solutions from TPTP programs, and you said that you have a tool which can verify that the solutions are correct.
Yes.
Have you tried to run it on those?
Not all, but a large fragment. So there's reasons why some of them still don't print out a proof, they just print yes.
Okay.
Right. But I can check that they're consistent with everybody else saying yes. And some of them print out proofs, but not in my language. So those I can't check. But for all the others I've done, I mean, I did it a few years ago, so I might be lagging a bit, but yes. And what I have had is I have found mistakes, yeah. And I can then, so the way I notice it is first I'll see a theorem prover gives a result that's inconsistent with the other 79 theorem provers, and I say, well, I don't trust you, but then I can take that proof and run it through the tool and find the position where the mistake is, and then I can go back to the developer and say, here, this inference is wrong, something, you've got a bug in that. And that's happened, well, it's not hundreds of times, but let's say tens of times.
So generally you are able to, when the proof is correct, that you can verify it.
Yeah,
it's
sort of it's a little funny. Some of the theorem provers do inferences that are hugely complicated.
Right.
And in those cases, so I'm testing the inference with the Otter, which is relatively weak, that's trusted. It'll say, no, I can't verify that step. And then my tool gives you a warning, I haven't verified this step over here. So we did this, I took proofs from E, from Stefan's, and then used E to check itself. So you take the big proof from E, and then get E to check each of its little inference steps. And even E couldn't verify its own inference steps. Results. That technology, I mean, the idea is also implemented within Spaß, crystal fiberglass stuff. Standard way to do things. I do a little bit more than they do. Yes?
Everything in the TPTP is provable?
No, definitely not. So we have things that are, a lot of it, say 70, 80% are theorems. There's a lot of things that are known to be definitely not theorems. And so if your theorem prover finds a proof, you've got a bug, because we know they marked as counter-satisfiable. Then we have things where there's no conjecture, you just want to check for consistency. So some things where a set of axioms which we know are consistent, and you can prove that they're consistent by finding a model. And we have sets of axioms that we know to be inconsistent. So you should be able to find a contradiction. So we have that sort of situation. And then there's a reasonable sized chunk, which is just unknown. No theorem prover's ever been able to get a result one way or the other. So they're in the rating 1 situation. For a lot of those, I expect them to be theorems because the person who gave them to me, mathematician or engineer, says, these should all be provable, because they've got some external reason for believing it. But if you can solve one of those, then you can definitely, I solved a rating 1 problem. I mean, Martin Suda downstairs, he loves doing that. Like, get one more problem that no theorem prover in the world has ever managed to find a proof for. And that's useful. And there's problems in there that are open from the human perspective. Things that are conjectures and no human has ever been able to prove them either. So the example is the Robbins algebra problem. That was open from Tarski, and when you get that, you get a paper straight away because you prove something really hard.
So how does it happen that you prove something which has been open for a long time? How is this?
Open for mathematicians?
Yeah, for mathematicians.
Okay, so once or twice, it's the one hand. It depends what you mean by open for a long time. There are some things that are being open but not attempted,
Yeah, but maybe not for a long time, doesn't it?
Yeah.
Like something interesting, which
Sure, so I would
like to, yeah.
So, I don't know, the AIM project, I think, is a good example of this is mathematics that's never been solved by a human before, and is not going to be solved by a human. They're not trying to. They're using, Bob Verhoff is using automated theorem proving to get results. So they haven't been open a long time, but they're definitely hard mathematical problems that if you didn't apply theorem proving technology, it would be unlikely that you could get the proof. I don't know to what extent, maybe you could pass on some papers about that project, or Bob's here next week.
Yeah, well, you could have mentioned David Stavsky also, like, just talked with you.
Right, David's work, yeah.
So he also proved an open thing about 10 years ago in algebra.
Yeah. And also there was the work of John Slaney in quasi-groups and semi-groups. They produced some new results in math that had never been achieved by humans before. That was in the mid-90s, late 90s as well. Finding new semi-groups with certain properties and things like that. And quasi-groups.
I guess it seems to be like like a kind of like a mainstream kind of thing, right? Which could be. So are we reaching the level of quality? So why is that happening?
Yeah, you answer me.
So
Up Joseph's line. Hold on.
Maybe what we should also say is that we can prove only very special problems, right? Not the calculus.
Yeah.
Like it's definitely not at the research frontier in many fields of mathematics, only in some very special.
So in algebra is of course strong, because in algebra is easy to encode in logic. And set theory, although I don't think there's any set theory result that's been proved that was open from a human perspective that I know of. And there's certainly some hard things that have been proved. But we were talking about this at lunch, is, computers yet have not reached the ability of the human brain to reason. That's what this research aims to progress. On the other hand, we do know that machines can go faster than people on the road because they drive quick.
Oh, yeah.
You talked about donation.
Sorry about?
You talked about donation.
Yes.
Dog. Who is currently funding the research or infrastructure? And how many engineers can you hire?
So currently it's me and one student. This has largely over the years been me and a collection of students as they've gone by, a lot of it myself. The hardware is funded by the NSF and my students is funded by the NSF.
I think you are not working on a concrete verification project yourself. How did you argue that you need infrastructure for your research?
So you can take like the star exec infrastructure you know about, which provides hardware for this, is what we have found between SMT and TPTP. There are enough people who are aware of this that the NSF see it as a valuable piece of infrastructure. And so we get it like that. So it maybe not that what we are doing is sort of the cutting edge of a science, but the cutting edge of science is reliant on us, so that NSF funds it under the infrastructure program. I don't know if that answered exactly. How would I get money to say that I'm doing science? I think it would be tricky. A lot of this is just grinding out stuff and keeping organized. The other things I do for which are more sciencey side of things, but that's different funding.
I was a bit wondering because I worked in a project which does verify certain systems used by somebody else.
Yeah.
And in that exact field, it was much easier to argue for funding because we have to prove this for somebody else. So that somebody else should pay there.
Yeah. It's rather what I'm having, is that I provide infrastructure that other people use to do their work. And that the NSF funds that, and they funded, the European Union funded me for a year, 14 months, to develop the higher order version of this. And that was developed at Max Planck. I think governments and research foundations see this as useful infrastructure that supports the other, sort of the application side of things. Gil.
You said that there were, we see that there were a lot of groovers, hundreds, at least tens.
Yeah.
So how many of them are strictly dominated by somebody's? I mean, how many of them idols or others? What's the diversity essentially?
I have to think about that. So if we take one of these slices of the pie, let's take sort of the common slice that everybody talks about, first order logic with some equality going in. I've got the data. Keep this alive. So actually I won't, let me answer. Is that there is probably somewhere around 30% are dominated. That's the sort of size. But what it is that there are some that are only just not dominated. They can solve one thing that's on the outside, and then the rest of the time they get slaughtered. So I would have to measure that, to what extent they're not dominated, but only just by doing one special thing. So there's provers written by people using strange technologies, like Blipsum Geo uses a geometric calculus. And when people do strange things, they can typically find some problem that nobody else can solve. Not because they're strong in the big sense, it's because they're weird, and they can go out into a strange little part of the TPTP territory. And so if I got them, then I say the domination is maybe more than 50%. More than 50% are dominated by somebody else. If I took up a strange outlier, some sort of half a standard deviation or something like that. So the big players like Vampire and E and Leo 3 in the higher order setting and CBC 4, big players who've been going for a long time really do tend to capture the bulk of the market. And so when you go to a recommender like mine, if I recommend something, it's very likely that you're going to be able to solve it with that one, and that nothing else would ever help you anyway.
All right, so let's thank Geoff again and move on to the part when you actually learn something. Or learn to do something.
Right, so this is aimed at the students, and you're going to need a pen and paper, or at least be able to keep a lot of stuff in your head at once. Because what I wanted to do, and this is just, maybe some of it's very simple, is look at going from propositional logic upwards, is how things are encoded, just to get a feeling of how you take a problem in the real world, and these are toy problems, and how you write them in logic, and then what we can do with them. And so if we start off with, let's just start with propositional logic here. And everybody's familiar, again, with Boolean algebra, propositional logic. Anybody know? Things are just true or false. And here's the story that I wrote, axiom and a conjecture, and I'll give you 30 seconds to read through that highlighted piece and make it bigger so it's easy to read. All right, and so the idea is, then, given that, how do you convert this into propositional logic? We take this first sentence, if the horse races are fixed or the bookies are crooked, then the tourist trade declines. And so here we have it in logical form. Horse races fixed or bookies are crooked implies tourist trade declines. Similarly, if the tourist trade declines, the police force is happy. Tourist trade declines implies police force are happy. Police force is not happy. Not. So you're seeing that. And then we want to prove that the horse races are not fixed. And again, I'm sure you can convince yourself of that by just looking at it. It's no huge mental gymnastics going on there. So the next step on that is, if you want to do this, is to write it up in TPTP format. So I want to talk a little bit about that so you can see the language and the syntax that people use. Specify the language, and this is in propositional as a subset of first order form. Every formula has a name, and names are useful because then when you write proofs, you can say the names of the previous formulas. Like when you use LaTeX, you give an equation number, but here I use names. Specify an axiom. So here we see the syntax, looks pretty much like the logic. Vertical bar for or, not the V sign, and it's not prefix. In some languages you use prefix or, and then the things that follow. So I want it to feel like English a little bit. Implies is the equals arrow and that. And so here, and end with a dot, so it's like if you're programming in your favorite Java language, semicolon is the end of a sentence. And here's the next one, tourist trade declines implies happy police, not happy police, and here we see the conjecture is that it's not the horse races are fixed. And the way you do this is copy it, take it out to the interface, put it in, and then, and I always run E because I like E, theorem prover, and away you go, goes off to Miami, electrons come from the beach, and a proof is found. Right, so that's easy. That's easy for everybody? Trivial, boring stuff. All right, so now, if you think that's easy, I give you 2 minutes to think how you would write out that problem in logic. better be thinking because we're going to do interaction now. Get that out of the way. All right, so this might be easy, but I want just to see, get people used to how I work with this stuff. You're on. What do I write now? How would I write this down? This highlighted sentence.
I don't know what to say. Quiet replicates resting.
Yeah, all right. So what you want to say is quiet. Whoops. Quiet implies resting, right? Like that? All right, next sentence.
Resting implies.
Okay, better put that lowercase.
Peaceful.
Resting implies.
Bracket, silent of bracket, peaceful and quiet and bracket.
Yeah. Okay. And then next.
Peaceful implies right first.
And the last one is the last sentence, the conclusion.
Peaceful implies
Peaceful implies.
and then quality or do I need to imply one side?
Yeah, right. It's not equality. Equality is between objects. You want equivalence, don't you? Yeah, right. So I told Joseph, I told somebody would do an implies, right? Right, like that, huh? Right, so then to make that into TPTP format, let's quickly doop, doop, doop. And this one has to be the conjecture. And we give them unique names to avoid confusion. And then put the closing bracket and dot. And that then would be the problem. So if I take that, let's see if you guys know what you're doing. Go to the interface. Oh, I'll use it over here. Don't want that. E is my favorite theorem prover. And go. Yep, all right. Okay, so that's easy. Now let's ramp it up a little bit. So we go to the first order logic. And here's the example I explained to you before. The USA is a country. So here, that's first order logic. Everybody familiar with first order? Still sort of there? All right. As we go on, it might get worse. The capital of every country is a beautiful big city. Here it is in logic. For all C, universal quantifier, if C is a country, then the capital of C is a big city, and the capital of C and is beautiful. So that's that. There is some city that is the capital of the USA, existential quantifier. There exists C, that C is a city, and C is equal to the capital of USA. So here we're talking about objects. That's when equality is right. At the higher order logic, equality and equivalence coalesce. Here we don't. And every big city has crime. For all C, if C is a big city, C has crime. A big city is a city. For all C, it's a big city, then it's a city. Conclude, there is some city that is beautiful. There is some, exists C, city C, and beautiful C, and has crime C. All right, so we get that. And then to convert that into TPTP syntax, wait, is it bigger here? Right, so we're going from the top. USA is a country, there it is. Here we have universal quantifier. My syntax is the exclamation mark. You will notice now that every character here is available on a standard keyboard. You don't need LaTeX to write in my language. You just need a good old Roman keyboard. For all C, C as a country implies Capital of C, big city. Notice here that variables start with uppercase, everything else is lowercase. It's Prolog compliant. You can read this stuff in Prolog with one read for Prolog programmers. Ampersand for and. Existential quantifier is there exists. And here's the equality, it's infix equality. If C is there exists a city, C, that C is a city and C is the capital, etc., 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 down to the conjecture. So we can take that, copy it, and put it into the interface. And push the go button. And voila, proof is found. All right, so now let's try the exercise on this one. Here it is down the bottom. Oops. I give you 2 minutes to read that. And then we'll go through and work our way around and see if we can do this. And then we'll move up to a stronger logic. We'll keep moving to stronger and stronger logics. Till we run out of time. Let's see, there's multiple ways to do this. Let's have a go at some of this. I'll get my editor up again. All right, so the first sentence, that one.
So we can say for every x.
For every x, okay, for all x. Yeah.
Good looking x.
We need some brackets here together. Yeah. So let's call it, we just put it good L. X, yeah.
Implies
yeah.
that there exists y that is parent of x and
parent x comma y like that, or do you want to say yeah? Mm-hmm.
Yeah, and good looking y.
Yep. Okay, everyone agree? Okay, I think that might work. Next sentence. Gentleman in the blue shirt. Would you like a new category? For all y. Yeah, don't worry about that. So you speak logic, I'll speak TPTP. This is not so.
Maybe we can speak just of oldest siblings, so that we can say.
Yeah, okay, I'll put oldest.
Oldest sibling y, that, and looking.
Like that?
Why is that?
Yeah, it should be oldest sibling of
y is that?
Is Z.
And looking that in class.
So it implies.
Oh.
No. What is pointed and why?
So say it. And
Looking that.
Okay.
In class.
Oh, so these two together, the and implies.
Exists a person which is good looking, which is okay.
then that somebody, that somebody is the somebody. It's the same. That somebody is that somebody.
Well, that's exists a quantifier and new variable looking at this, right?
It's the same person from earlier. All right, we've got a debate here. The input from here, sir. Huh? Good looking Y. And also what's happening is now Z is an unquantified variable. The Z, should it be universal? Yeah, good help. Yeah. I think, and you need Z to be for X and Y. If the oldest sibling of Y is Z, and that Z is good looking, then Y is good looking. So if your oldest brother is good looking, then you are good looking. That's roughly what you're saying. All right. So it's not quite so easy. Let's try. No. I was trying to say that somebody is the same as that somebody. So then it's the same variable. All right, next sentence. The only parents of Jeff are Bob and Maggie. Next. We need something to say about parent of Jeff.
Jeff Bob.
Yeah.
And father Jeff Nancy.
Yeah. And now that says Bob and are my parents. I want to say they're my only parents. No, I could have other parents. It's Miami. I mean, all sorts of stuff happens.
I mean, if you only use these two, then.
No, so, all right, we can leave it out, but you'll find you can't do it then. You have to say, it's like we did on Agatha. They're the 3 people who live in the mansion. They're the only people who live in the mansion. You do need to make it, otherwise you can find a counterexample where somebody, I have a third parent, maybe a stepfather, and they invalidate the argument. So how do you say these are the only parents? Here's how you do it. I'll show you. For all Y, if the parent Jeff, Y implies Y equals Bob or Y equals Maggie. That's how you, that says they're the only ones. All right, this is going on in such a time, and I've only got a couple more minutes before beer break. And so you can see that this becomes a little more, but it's still possible. You get the feeling, but you have to be careful about thinking about these things. So what I want to do is just go to one more logic. And if we go back to this example here, where we talk about city, we often talk about things that are coming from a set of things, a type of things, cities, peoples, integers, rationals, furnitures, like that. And so the next language up, which is type first order, allows you to specify the type of something, its data type, as you would in programming languages. For the ML programmers out there, you know, an ML program, they say that if you pass the type checking, your program is correct. You don't need to know anything else, as long as the type checking works out. So here's a little example that shows you how you can use types. And this language I found to be very nice because it's still got that simplicity of first order, but the type checking eliminates mistakes that people make. So here it is. All humans are created equal. John is a human. John got a fail grade. There is some human who got an A grade. An A grade is not the same as a fail grade. Therefore, there is a human other than John who was created equal to John. That's kind of nice. This is, you see, this is coming from America. All men are created 407 years ago. Like that. So here's what we do. We've got 2 types of things here. We've got the human type and the grade type. So you need to determine what types you want and then assign everything a type. John is of type human, A is of type grade, F is of type grade. And for every function and every predicate, you specify the type signature, just like you would when programming in any regular programming language. Type program. So created equal takes 2 humans and returns a Boolean. grade of takes a human and returns their grade. So here's how you write this in logic. Right? For all H1 of type human, for all H2 of type human, they are created equal. So you notice the data types are declared for the variables in the quantification. The grade of John is fail. There exists H of type human such that the grade of H equals A. A is not a fail. Therefore, there is some H of type human who is not John, but was created equal to John. So in the TPTP language for this, and this is where I have to stop, is you have to define your types to be of this funky thing called $T type for historical reasons. Anyway, so human is one of our types. Grade is one of our types, so we've got two sets and two things in the world. John is a human, A is of the type grade, F of the type grade. You'll notice that all of these have the type declaration. Say this is typing information. Here we have the declaration of the predicate created equal. It takes a human and produces $O. That's the built-in type for Booleans, true and false. And grade of takes a human and produces a grade. So now we can see this. Here's all humans are created equal in TPTP syntax. For all H1 of type human, H2 of type human, created equal H1, H2. So it's very much like you would write it, but there's some syntax for this. And we can put it all together. Then as before, you can grab all of this material and go into system on TPTP. Whoops, daisy, I'll go over here. Just go back. And now I'm trying to think which theorem prover can deal with this stuff. Well, I know. But of course, if I didn't know, what do you do if you don't know which theorem prover can deal with your problem? Push the recommend button. Da-da-da-da. And it tells me a whole bunch of them that would do it. Even Z3 apparently. Let's use our favorite vampire. And if you don't want to do it, you can just push the run parallel button and it will do parallelism. But we'll take vampire version 4.3, push the go button, and again we get a proof. And so if you're interested in playing with this, I've got more examples of these if you want to try them out. Here's an example in type first order. For people to play with, maybe you can do this. This should be your next lecture.
Yeah, or maybe you can
do it as homeworks. Homeworks. Do all of them. And then for people who are interested, there's stuff in higher order logic, which then gives you lambda abstractions, and there's also a polymorphic version of this. And so you can look at this example if you're interested and see the higher order logic, which enables you a stronger language for writing things, but it's harder to write it down. You can really, this stuff starts to, I mean, Chad and these guys just talk higher order logic like it's casual stuff. It's just sex to them. But for me, my brain starts to hurt. And I've given a challenge example there as well. All right, so that's the homework for the students to complete all of those.
Thanks a lot.
Okay, thank you.